That's not the one. There we go. All right. Make sure this time I have the right mic on. 1 sec. Yeah, we're good. Okay. So real quick. So these are the notes for 5.1. Now, all the exponential function means is it's some number greater than 0, not equal to 1, of course, because that would be boring. So some number raised to the x power. So the x is going to be what varies, which will make it grow really quickly, right? You've all heard it's growing, the phrase, right? It's growing exponentially. So you can see right here an example. Let's see, no, that's not a good one. I think I'll just show you a graph in a moment. Here, check this out. So 2 to the x, if I put in a 2, well, obviously, if I put in a 1, it's going to be 2 to the 1, which is 2. If I put in a 2, it's going to be 2 to the 4th, and it becomes 4. So pretty quickly, it starts to go up. If I put in 3, well, it's going to be 8. Plug in 4, 2 to the 4 is 16, and it keeps growing really quick. So you put in 1,000, it's going to be humongous. 4 to the x is a bigger number, so it'll grow a little faster. As you can see, it has it's closer to the y-axis because it's growing faster. Okay, now, if you use negative numbers, it gives you smaller and smaller fractions, so it's decreasing. Okay. Now, a to the x or a to the negative x. So if it's negative, then it's just reflected the other direction. So let's do some quick graphs here. Now you can see as x increases, the y goes up pretty quickly. But if I plug in negatives, it starts to approach 0. Although it never gets there, it gets infinitely close the more negative you get, but never hits 0. There's an asymptote underneath. Now, if you have a minus here, it's just going to be reflected. So as you plug in bigger numbers, it approaches 0. When you plug in more negative, it shoots off. So it just does the opposite. So on the homework, they're just going to start you off by just try plugging in some numbers. So here's 0.5 to the x. Well, plug in 1.3, see what you get. So it's nothing crazy. They just want you to get comfortable. Oops. .5 to the x, plug in 1.3. So if x is equal to 1.3, sorry, f of x, so 1.3. They want just this number. That's all. So they just want you to get comfortable, plug in the numbers, see what happens. Okay. Nothing crazy. Any questions about that? Does that make sense? So do you understand what the exponential looks like, and can you plug in numbers? Okay. So here they just want you to plug in some values and then choose the correct graph. You can sketch it with some numbers, so it's just not a big deal. I just want you to get used to the exponential. Okay, now if it's shifted upward, obviously you have a what's it called? Asymptote at a different spot. But usually if it's not shifted vertically, it's going to be an asymptote at 0. Parabola right there. Okay. So there's not much to do here. It's more like, do you understand what an exponential function looks like? The domain is negative infinity to infinity. You can plug in whatever you want because there's no issues plugging in any number. You can plug in whatever you want. The range, though, will depend if it's shifted or not. Usually, if it's just a regular a to the x, again, we said there's a asymptote at 0, y equal to 0. So it can't cross it, but it approaches it. So that's and there's no bracket, and it shoots off upward, so to infinity. Y-intercept is 0, 1. So 0, 1 right there. So as a to the x approaches 0, x approaches negative infinity, so that's the asymptote we're talking about. So this function is continuous everywhere. You can plug in any number. So this is really all you need as a summary for a general exponential. Okay. This property here, though, is important. They're saying that if a to the x is equal to a to the y, oh, excuse me, if a to the x is equal to a to the y, this will only be true if only if x is equal to y. So this is pretty important. We're going to use that later. This is saying that if and only if statement, whenever you see that, you change the mind. So whenever you see if and only if statements right here, that means it's true in both directions. So if this is true, then this is true. In other words, so it can go this way or that way. There's a powerful statement that basically says that if I have an equation, let's pretend I say, well, you know what, if x is equal to y, then that means I could introduce any base that I want, as long as it fits these conditions. I can bring an a underneath and bring an a underneath. So, meaning, so if I have, like, let's say, I don't know, x equals 7, then I could say, well, that means I could choose any base and bring it, create an exponent, make these into exponents. Does that make sense? And vice versa. If this is true, then I can come back here. Or if I have this, I can choose whatever I want underneath. Make it a 4 or 3, who cares? It's a very powerful statement, and we're going to use it, I think, later. Just a moment. Let's see if it comes up. Oh, here we go. He wants to use a property for 16. So basically the property said, if the bases match, then I can set the powers equal to each other. Or if I have an equation, I can choose a base of whatever I want, as long as it's not 0 or 1. So change the 16 into a 4. To rewrite that as 4 squared, right? Now these match, and the formula says, well, if these are the same, then I can set this. You can set the powers equal to each other. Does that make sense? So that's all you do. So the first 70% of the homework is just kind of playing with the function itself, plugging in numbers, looking at graphs, understanding the domain and range. And then we get to exponential equations. And we just want to match up the base. Force it, if possible, match the base. So right here, before we move on, any questions on 15? Yeah, exactly. It said that the following is equal. So if you have x equal to y, then you can say a to the x is equal to e to the y. Vice versa says the other way is true. But if I have two exponent stuff like this, and the bases are the same, then I can set the powers equal to each other. Yeah. So use the one that helps you, right? And these examples we're using the second one. So I'm breaking the if and only if statement into two separate if then statements. Okay. Now 16. How do I change this 1/4 into, because this one's easily a 4 squared, right? We just did that. So I can start off with so I need to make them both 4. So how would I fix it? Do you remember these rules of exponents? Yeah, I need to change the 1/4. So I can force the power to the top to make it a 4 instead of a 1/4, but then whatever power it has will become negative. I can say this right here. Almost there. Now I have a power to a power, so that becomes you multiply, right? When you have a power to another power, you multiply. So now I can say negative x is equal to 2. So x is -2. So the rules of exponents will be very helpful in this section. And this star and double star too, of course. Okay, any questions on 16? That makes sense, what we did? Okay. Let me know if you have a question. Yeah, I would have them at the ready to help you out. There's another one that needs that idea. So make them both into 5s. We should know that 125 is the same as 5 cubed, right? Oops. So what would that right hand side become? I need to fix that side.
Five to the power of -3.
Yeah, exactly. Now they match. So you can use that rule and just set the powers equal to each other. So x would be 0. Any questions on 17? All right. Number 18, they just want you to plug it in. Notice how they're using the E. That's nothing special. E is just a number like pi. Pi is like, right, 3.14 something. E I think is 2.17, I think. Forever. So it's just a number in your calculator. So this is like almost 2, I guess. So plug it in your calculator and you'll get your answer. There's nothing really to do here. Nothing at all. We plug this in to here, to the X. There should be an E to the an E button, so just press E to the 2.6. Not much to say. E is a very special base that we like. It comes up a lot in like physics, engineering, and I think biology too. And when we start measuring growth, it's called Euler's number or the natural number, and it comes up a lot when we're modeling like bacterial growth or population growth. This is an interesting number. You know, we find it during calculus, but for now, just think of it as a special number like pi. Don't worry too much about it. So here we have matching bases. The base is about 2 point whatever. So since they match, what do we do? Yeah, same thing. There's one. Over here, same deal, except you're gonna solve a quadratic. So you would just solve this. Anyway, I'll let you solve the quadratic on your own. Okay. 24, 25, 26. It's talking about interest. Let's find the interest formulas. Here is the interest for compounding n times per year. Hold on, sorry guys, 1 moment. All right. So this is the formula we're gonna need. R over n to the nt. R is gonna be, well, let's see if we have it here. So n is 1. So we need to use this formula. Together P, R, and Q. So just change the n's each time. It'd be good. So compounding once, that used to be once a year. And when n is 2, that's twice a year. N is 4, it's 4 times a year. So if they say semi-annually, they mean twice. If they say quarterly, that's gonna be 4, etc. Okay, if they say daily, you're gonna use this. Okay. Now, if they say continuous though, you need to use this one. So in calculus, when they let the compounding go to infinity, this will turn into an exponential function. So this continuously compounded all the time, right there. Okay, does that make sense? So for number 1, or the first one. Just, well, that's kind of boring. Let's do the 2. So it'd be 2,000 times over 2. N is gonna be 2, so it'll be 2 times t, so it'll be 2 times 10. So just change the 2 to whatever n we're talking about. Okay, all these n's right here. Does that make sense? So just use this formula whenever they mention compounding. For the last one, this should work. It should be 2,000 e to the RT. Are there any questions on how to input it on the calculator or what the pieces mean? Okay. It's pretty straightforward, right? It's not too crazy. You'll need a scientific to get this. I don't have one on me right now. But that's pretty much it. Here, they want you to see how time affects growth. Yeah, just play in the right spot. That's it. So they said continuous. So which formula do we need? Yeah, that first thing. So just plug in your 10,000, or sorry, what is it? They invested 12,000. And they want you to see how much money you get in 10, 20, 30, etc. years. Rate is 4%. Make sure you change it to 0.04. Always divide by 100 to change to decimal. Times your t. So just oscillate the t's. All right. Number 26 is the same type of deal. So let's move on. Same thing. Okay. I think it's time to move on to something else. You guys have any questions on these concepts? The big picture is, do you know what an exponential function looks like? Can you plug its numbers in? Do you know if the domain and range? Can you use these interest formulas? All right, let's look at logarithms. 5.2. So this formula right here is going to be important. It's also an if and only if statement, so both directions are true. So y equal to log a to the x if and only if x is equal to a to the y. So this is the definition of a logarithm. You can change an exponential into this form. So you read it as log base a of x. So the bases are right here, the a. Just need to make sure you know how to switch back and forth. Okay. For example, 9 is equal to 3 squared. If you change this into logarithmic form, you get 2 equal to log 3 of 9. So look at where all the base is, right? The base is 3, so a is 3, a is 3. X is going to be 9. So 9 is equal to 3 squared. So the first few questions in the homework, I believe, are going to make you just shift back and forth. Here. So here they're giving us an example how to change an exponential to logarithm. But let's do this guy based on that definition. Oops. Okay. So the base is 2. So it's going to be same as this, right? So it's going to be, let me think here, 2 to the 2 is equal to 4. So you're going from exponential to, sorry, going from logarithmic to exponential. And it helps to see this, or writing the formula down, of course, but this kind of helped me because I don't have that thing memorized. Any questions on 7? Is that straightforward? We're just using a definition. All right. Let's move on to something else. Eventually you start solving equations. So let's find those. I could do 13, I guess. . But without using a calculator, plug in 16. You get log 2, 16. So if I change it to log 2 of 2 to the 4th, these 2's will undo each other. You'll be left with only the exponent. Well, let's look at the formulas. I think the formulas are in there. Here we go. Properties of logarithms. I think it's in the property sheet that I sent you guys a list of properties, right? I feel like I did at some point. I don't remember. Okay. Let me see if I can find it. If not, I'll just have to log into my personal computer and send it to you guys. It's, this blue one, is this familiar? See if it lets me download it. All right, let me throw it in the chat so you can download it. Save that file. Print it whenever you want, and you can use it on exams too if you like. But it has the exponent properties from I think back in the day, I think high school, maybe middle school. And it has the basic properties of arithmetic. Right here, though, it has the logarithmic properties. That first one we just talked about doesn't have that one we used earlier, but it's all good. Okay. There, I lost my train of thought there. So when the log matches when the bases match, they will cancel out. You'll see it here. If I plug in a to -2, inside the logarithm, the log a and the a would undo each other because they are inverse functions. It's kind of like when you do square root of x squared, they just cancel out and give you an x. Same thing, because they are inverses, they cancel, leaving you with just the power. All right. Log base of, oh yeah, they match up and there's no power. That's just going to be 1. I believe that's right here. Log b of b is 1. If you plug in 1 to any logarithm, though, it's going to be 0. And here's another one. If it matches, you're left with just the exponent x. Vice versa, if you raise, if you put the log in the power, they'll also cancel, leaving you with the argument x. So here we said you're plugging 1 into anything, it's going to be 0. So they're just kind of testing you on the properties, see if you know them, or if you can just refer to them, it's fine. Here they're going to cancel. So what do you think 21 is going to be? Yeah, it's just going to be the argument 10. So look at the formula sheet. That one. Here, see if it's b to log b, those get undone, leaving you with x. Our x happens to be 10. Any questions on 19, 20, or 21? All right, so now we're moving on to something else. Yeah, I guess that's true. It looks kind of like it's timed, right? That's fair. Okay. 22, what I want you to do is raise both to a different power. Or sorry, you're going to change these into a power. So the 1-to-1 property we wrote down earlier, we're going to use it in reverse to cancel the logs. And I don't want you to use this rule because it's better to do it the way I'm going to do it right now. Let's see if I see it. Well, I don't have it in here, but it's probably in the notes. Here, see number 4. I don't want you to use 4. I prefer you do it this way. Let me show you. I mean, you can just remember this is better long run. So if they don't mention a base, notice how there's no base on this log. It's assumed to be 10. Just like square root, they never write the 2. It's assumed to be 2. So here it's assumed to be 10. So what I want you to do is just remember that if you have an equation, right? Then a to the x is equal to a to the y. So I'm going to choose a base a to help me. So I have log 12 equal to log x squared plus 8. So introduce the base that'll help. So I'm going to choose 10 and make these the powers. So now 10 will cancel log base 10. I know that the number 4 rule would have been easier, but this will be better in the long term because you won't always have logs. You might have a number or something or some X term, just depends. So then these cancel out, leaving me with 12 equal to x squared plus 8. Then I'll solve the quadratic. Running out of space here. Actually, subtract the 8, that would be 4. Square root both sides, you would get plus or minus 2. I skipped 2 minor steps. Let me know if you want to see them. Once you solve for x, though, you should test both and plug it in to your equation for all x's and see if you get equality. Because you have a log, when you have logarithms, you might have a number that you can't plug in because you cannot have 0 or negatives inside or something that results in a negative or a 0. Okay. But any questions on the process? You see what we did, right? Here they're asking for the domain and range, so make sure you understand what the graphs look like. I'll talk about it, I think, down here, graphs of the log functions. So they are inverses of each other, so when you graph them, you'll see that they'll be reflected across the y equal x right here. Alrighty. But there is a vertical asymptote. Remember we said you cannot plug in 0 into the log function. So it can approach 0 but never get there. But you cannot use 0 or negatives. But the smaller fractions you choose, the more negative the output becomes, but no negative inputs. So this is the information you're going to need just to know what they look like. The domain and range, we said the inputs must be above 0, no zeros are allowed. Range will be everything because it goes up slowly, but eventually hits everything, and it goes down as well. Okay. Intercept is usually 0, 1, or sorry, 1, 0, unless it's been shifted, which is the inverse from the exponential, where their y-intercept is 0, 1. So they'll test you on these concepts like, all right, do you know the domain? Do you know this or that over here? So they either graph it and just look at it and say, okay, well, or remember that you cannot plug in 0, so it has to be above 0, and then it keeps going forever. x-intercept we said is always going to be for any base, as long as it's not shifted, it's going to be 1, 0. Vertical asymptote, we said x equal to 0 because you can't plug in 0, it just approaches it. All right. Any questions? Seem doable? Oh, here we go. One last thing, I guess. Ln is the inverse of E. So it's just a special base. So just real quick, I think in the book or other math books, they say log base E of x is equal to ln x. They call this the natural log. Supposed to be an L right there. Log base 10 of x is equal to just log. They don't write it, the 10. They call this the common log because it's the one on the calculator. If you look at your scientific calculator or graphing, you'll see they have a log button and a ln button. But the ln means base E, log means base 10. That's all. It's just a shorthand because they don't want to write E all the time. So when you see this, they're saying log base E. But we already said earlier, if you plug in 1 to any logarithm of any base, it will be 0. Hence the statement. But if you use the definition to change it to exponential form, you can do that like we did before. Oops. Any questions on logarithms? So far. I think we might have to do that one. 32. Oops. Yeah, let's do 32. You look at the properties. He said if it is being subtracted, look at the last one right here. You can change it to division. Okay. So, sorry, I'm spaced for a second. So use the rule, since it's subtraction, you can change it to ln of 1 minus ln e cubed. Because the rule says ln of a over b is equal to ln. This is for any log, not just ln b. Remember the property of whenever you plug in a 1, this will be 0. And these match, leaving you with a 3. So this will simply be -3. So use the properties of natural logs. Well, I should say use the properties of logarithms. That's it. All right, so not too bad, right? The same as before with the graphs. Here they want us to solve. But y'all see what the base of E is going to be? Or sorry, Ln, right? You see it's going to be base E. So for both 34 and 35, introduce the E base to cancel. These are gone. So solve for X. Just make sure you test it to see if it works. Track 9, you get 6, right?
Yes.
So if I plug in 6, is that a problem? It looks fine. We're good. Yeah. All right. We're about done with this section. So far, do you guys have any concerns or questions? Do you see what they're doing? Okay. It'll get a little harder on 5.4. We'll be using a lot of the properties, so try to get comfortable with all the log properties and exponent stuff for next time. 5.4 will be a little more involved. And I think that's the last section for the next test, which we'll figure out as well. So I'll try to give you more time though. Let's see here. Unit C is not due till 27th. So try, like I said, remember, get that out of the way as soon as you can, because the next one's coming up shortly after that. All right. You guys have any concerns or questions? Okay.